The third property of water is basically that ice floats. Now before we look at water, let's take a look at other substances. As a gas, most substances are spread out the most with the molecules moving the fastest, typically the least dense. Liquids would be the next dense, molecules moving less fast. And solids are typically the most dense, with the molecules moving the least quickest and more close together. Now, water is a strange substance because it doesn't follow that particular pattern. The gas obviously is the most spread out, the least dense, and then we actually have a solid. We have ice being less dense than in the liquid form. And again, like all of our other properties so far, this goes back to water's polarity and its hydrogen bonding. When we see water in a solid, when it's frozen, all of that means is that the water molecules are not moving fast enough to break the hydrogen bond, so they don't have enough kinetic energy. In liquid water, they're moving quick enough that those hydrogen bonds are breaking. In a solid, when it's frozen, those hydrogen bonds are kind of forming again. And that usually happens typically at 0 degrees Celsius, and water forms this crystalline structure. And this actually has the water molecules more spread out, if you look here distance-wise, than in a liquid form. So solid water, in other words ice, is less dense than the liquid, which is totally opposite of most other substances. So therefore, ice floats. And the purpose of this, or I should say the importance of this, is that when bodies of water, whether it's a stream, a lake, an ocean, when ice freezes, it's freezing from the top down, and it insulates the water underneath, allowing organisms to survive underneath. Otherwise, if ice did not float, most bodies of water would freeze solid in the winter and we would not see much life. So that's our third property of water. It's probably the easiest and the one that everyone really remembers. Now, our fourth and final property of water is that water is a very versatile solvent. Now, what does that word actually mean? In a solution, we have the solvent, which is the substance that's doing the dissolving. Typically, we think of that as being water. And the solute is the substance that's getting dissolved. When the solute is dissolved in the solvent, it makes a solution. Now the word dissolve, let's take a look at that word more closely. Scientifically, what the word dissolve means is that water will surround the particles in that substance. And just as we said a few minutes ago, this property of water again goes back to its polarity and its hydrogen bonding. So let's take a look at an example of an ionic compound dissolving in water. Over here in green and yellow, this is a salt, typically or most likely sodium chloride. And as you can see, the ions are being ripped away from the salt and being surrounded by water molecules. That's what the word dissolved means. The components of that ionic compound are being ripped away from the compound and being surrounded by water. Now, as we've talked, this side of the water molecule, the oxygen side, has a partial negative charge. And notice that the partial negative charges are all facing this ion. So we can assume that this is a positively charged ion. In this case, this would be sodium. This ion over here, we have all of the positively charged, or the partial positives, facing that ion. So we can assume that this ion over here is the negatively charged chlorine. And when water surrounds a substance, we say that that is a hydration shell. So this is now being dissolved, the solute is being dissolved in the solvent. Now, ionic compounds aren't the only things that can be dissolved in water. Water can also dissolve other covalent compounds, but the key idea is that the covalent compound has to have polar regions or be polar overall. For example, this is a really large protein called a lysozyme, and when we place it in water, you can see that there's a hydration shell, water molecules all surrounding the purple protein. Again, we can assume that this purple protein is polar because we have the water being attracted to those regions of the protein. So this protein, even though it's large, can still be dissolved because of those polar regions. Now, the only things that cannot dissolve in water are non-polar substances. And thinking about why, dissolving, all that means is that the water molecules are attracted to and surround the substance. Non-polar molecules have no charges, so there is no physical way that water can be attracted to anything if there is not a charge on it. Now, you may hear me refer to these as polar and nonpolar things, or ionic and polar and nonpolar, but this is probably what you'll hear me say more often. Substances that can dissolve in water that are attracted to water are polar or ionic, or more commonly we call them hydrophilic. Substances that are nonpolar and do not have an affinity or an attraction for water are hydrophobic. Now, when we study the cell membrane, the phospholipid bilayer, we're going to see that each phospholipid, each little thing that looks like a little guy, has hydrophilic regions and hydrophobic regions. So the hydrophilic heads face the water because they have an attraction and an affinity for water, and the hydrophobic tails face away from the water and are on the inside of the cell membrane, away from any aqueous solutions. So you may hear me refer to those as being hydrophilic, hydrophobic, or polar and nonpolar. So that was our fourth and final property of water. Now going into that a little bit more in depth. When certain substances are added to water, this is all happening in an aqueous solution. So biology is basically just chemistry that's going on in water. So anytime we study a reaction, keep in mind that most of these are happening inside the cell, inside aqueous solutions. Now, I'm not going to lecture on this section, but just take a look at some things that you did in chemistry, converting moles to grams, grams to moles, what molarity is, and just kind of take a preview of this. In this summer assignment, I do have one worksheet that you can kind of practice doing these, and I will post the answer keys to those eventually, just so you can kind of get some practice doing those types of chemistry problems again. Now, taking that idea of aqueous solutions a little bit further, depending on what we add to the solution, we can make a aqueous solution either acidic or we can make it basic. And what we have to look at is this reaction called a dissociation reaction. Now, when we typically think of water, we think of it as being the water molecule H2O. But at times, the hydrogen and the oxygen atoms will separate from each other. So let's take a look at this visually. It makes a little bit more sense that way. So here we have two water molecules. At times, this hydrogen atom will be removed or will move from this water molecule and move over to this water molecule. When that happens, we say it dissociates, and this is a hydronium ion, but for the rest of this lecture, we're going to be calling this hydrogen, or the hydrogen ion. This is the hydroxide ion, which is OH negative, and this reaction of when the hydrogen leaves one water molecule is dissociation. If we add any solute to a solution that increases the amount of hydrogen ions in solution, we say that that is an acid. If we add any substances to a solution and it reduces the concentration of hydrogen ions, we say that is a base. So that's exactly what you'll see on the next slide here. In pure water, that hydrogen ion and hydroxide ion concentration is equal. But adding certain substances, certain solutes, can shift those concentrations. If something increases the hydrogen concentration, we say that that substance is an acid, and something that would reduce the hydrogen concentration would be a base. So let's take a look at a few examples of each. So for example, if we take hydrochloric acid and add that to water, it's going to dissociate into hydrogen ions and chlorine ions. Because this hydrogen ion, and again, this is going to be many ions, is being increased, the concentration of hydrogen ions are going to be increased, we say that this is an acid. So we would have a very high concentration of hydrogen ions in comparison to hydroxide ions, so the whole solution would then be an acid. Now let's take a look at two examples of bases. If we take ammonia and add that to water, it's going to add or bond with some of the hydrogen that are already in solution, so it's going to remove those from the solution and become NH4. So again, the hydrogen ion concentration is decreasing, which is the definition of a base. Another example, sodium hydroxide. This is going to dissociate into sodium and the hydroxide ions. The hydroxide ion is able to go and bond with the free-floating hydrogen ions and remove those from a solution. In other words, reducing the concentration of hydrogen ions in solution. So if we go back and look at our definitions again, those are the exact definitions. Acids increase hydrogen ions, bases decrease hydrogen ions. So the pH scale is a scale that scientists use to measure the amount of hydrogen ions in solution. The higher the concentration of hydrogen ions, the more acidic, and the lower the concentration of hydrogen ions, the more basic. And we can actually do some calculations with this. Again, if we have pure water, these two concentrations are going to be equal. But if we are trying to figure out what the actual numeric pH is, we can use this equation right here. pH is equal to the negative log of the hydrogen ion concentration. So for example, in pure water, in a neutral solution, the hydrogen ion concentration is 10 to the negative 7th. So if we plug that into our calculation here, that's going to give us a value of 7, or a pH of 7. If you look at our pH scale, that's right in the middle. Now, if we have increased concentrations of hydrogen, so if we change this number, let's say to 10 to the negative whatever, we're going to see that that's going to be a very low pH. So 6, 5, 4, 3, 2, 1, 0, those are very low pHs, very acidic, further away that we get from 7. The opposite side, as our hydrogen ion concentrations are decreasing, our pH value would be high numbers. These would be considered bases. Now, even though this is a scale that it goes from 0 to 14, remember this is a logarithmic scale. Every jump on the pH scale is equal to 10 times difference in the concentration of hydrogen ions. So for example, a pH of 6 versus a pH of 4. A pH of 4 is 10, so 100 times more acidic, 100 times more hydrogen ions in there than there would be at a pH of 6. So just keep that in mind, that even though this goes 0 to 14, we're still talking about 10 times difference in hydrogen ion concentrations with every step. Now, in biology, systems typically have buffers in place that will minimize changes in those different concentrations of hydrogen ions and hydroxide ions. Usually this is consisting of a weak acid-base pair that can reversibly combine with hydrogen. So for example, if we look at ethanoic acid, this reaction is reversible. Okay, so it can go either direction. If an acid is added to the system, so let's say it's added to the cell or whatever we're talking about, the reaction is going to be shifting to the right. So we're going to be making more of this compound. Now, if a base is added, if our pH gets too high, the reaction is proceeding in the opposite direction. Okay, so we're going to end up seeing more of the hydroxide ions taking the hydrogen ions out of solution and making water out of it. So we're going to neutralize that pH. So buffers are typically reversible reactions that can go in either direction, and they will shift either direction based on what is added to the solution. So that concludes our review of basic chemistry. Again, make sure you're completing the worksheets either as you're watching the videos, as you're reading the text, or both. And also complete those other packets that I've included. Answer keys will be posted shortly, And reminder, you will be having a quiz on this during the first week of school.